Welcome to the responsive equilibria to conditions. So, an equilibrium responds to changes in pressure, temperature, concentration of our reactants, concentration of our products, and an equilibrium does not respond to a presence or absence of a catalyst or an enzyme. So remember that a catalyst or enzyme gets us to an equilibrium faster, it increases the rate, but it doesn't change the equilibrium position. It doesn't change the equilibrium composition that we will get. So remember that delta Rg naught, so the standard Gibbs energy of reaction is equal to minus RT times natural log of K. K here again is our equilibrium constant. So the value of K depends on the value of delta Rg naught, which again is defined at a single standard pressure. So since delta Rg naught is independent of the actual pressure at equilibrium, the value of K is independent of the actual pressure at equilibrium. So that means that at constant temperature, the value of K is a constant. It doesn't depend on anything else. Because if we go back here, our value of delta Rg naught appears to change with temperature and our equilibrium constant. Well, if temperature is constant and delta Rg naught is constant, then K must be constant. So as long as we keep the same temperature, our value of K is the same. Note, however, that while our equilibrium constant is independent of pressure, the equilibrium composition might not be independent of the pressure. The constant is independent of the pressure, but the actual composition that we have, the actual ratio between our products and reactants may, or rather, the actual numbers of reactants and products may vary. So this box is supposed to have a double-headed arrow in it. So if we look at composition, or at an equilibrium between two ideal gases, so we have A that's decomposing into 2B. So we have a case that looks something like this. So if the pressure is increased by adding an inert gas, so we have, look at the cylinder on the left. So over here, if we have our reactants in there, and some reactants and some products, and then we put in some other inert gas, some species that won't react, the partial pressure of A and partial pressure of B remain the same. And that means that the equilibrium composition doesn't change. Our partial pressures aren't changing if we put in an inert gas. We're changing the overall pressure, but we're not changing the partial pressures of A and B. So we're not going to change our equilibrium composition. But if the pressure is increased by decreasing the volume, so if we go from this state to this state, if we squeeze our container, now our partial pressures of A and B change. So know that the ratio between our partial pressure of A and partial pressure of B doesn't change when we squeeze our system, because they're both changing by the same factor, however much we've changed our volume. If we have our volume, then our pressure is doubling. If we double the volume, then our pressure is being halved. But so the ratio between our partial pressures doesn't change. But the equilibrium constant doesn't necessarily scale with that ratio. So in this case, we have 2B being produced for every A that gets destroyed. And so now we have our equilibrium constant is the pressure of B squared divided by the pressure of A times the standard pressure, so 1 bar. So that P naught is 1 bar. So the right side, this fraction here, is constant only if our increase in partial pressure of A cancels an increase in the square of the partial pressure of B, which won't happen. Because remember, we said the ratio between partial pressure of B and partial pressure of A, this value is a constant when we squeeze our system. But if this value is constant, then that means this value cannot be constant. So, our value of K there has to change, or we have to change our pressures. And we know the value of K can't change, so we have to change our pressures. We have to change our ratio between the pressures. Right? So this means that our ratio of the partial pressure of A, the partial pressure of B, has to increase. Or the partial pressure of B, the partial pressure of A, has to decrease. So this means that our equilibrium has to shift, our equilibrium composition has to shift towards A. So if we have A in equilibrium with 2B, and we squeeze our container, so we're increasing the pressure, our system is going to try to respond by Le Chatelier's principle to remove that extra stress, to remove some of the gas molecules that will shift us over towards the A mol, towards the A side, the reactant side. So this is a special case of Le Chatelier's principle. So again, our system at equilibrium, when subjected to some disturbance, responds in a way that tends to minimize the effect of that disturbance. So our system is trying to minimize the effect of raising the partial pressures of A and B. So if our system at equilibrium is compressed, then our reaction will adjust to minimize the increase in pressure, and it can do this by converting some of our B back into A, right? Because for every 2 molecules of B that we use up, we're only producing 1 molecule of A. So let's examine this effect of compression quantitatively. So suppose we have some initial, initially some amount N of A with no B present. So we're going to let alpha here represent the amount of A that reacts, and at equilibrium, where the amount of A present is then 1 minus alpha, so the amount that we have left is what we started with, 1 minus alpha times number of moles N. And this means that the amount of B present is 2 alpha N, so twice the number of moles of A that reacted away times the number of moles of A that we had originally. And now that means that the mole fractions at equilibrium can be given by these 2 equations. So the mole fraction of A ends up, after we do some math, as 1 minus alpha divided by 1 plus alpha, and the mole fraction of B is 2 alpha over 1 plus alpha. So now we can use Dalton's law of partial pressures. So again, here's Dalton's law of partial pressures. The partial pressure of A is equal to the mole fraction of A in a mixture times the pressure of the whole mixture, the total pressure, and the pressure, similar thing for B. So the pressure, partial pressure of B is equal to the mole fraction of B in the mixture times the total pressure of the mixture. So we can use Dalton's law of partial pressures to relate the partial pressure of A and the partial pressure of B to our total pressure P. And this means that we can obtain the following expression, right? So we're going to go through some math here. So we're going to start out with our K, our equilibrium constant. We're going to plug in for our pressure, so PV and PA. We're going to plug in these 2 equations of these sides. So we're going to start there, and we're going to go on here. After we do some math and clean it up a bit, we end up over here with 4 alpha squared times the total pressure divided by the quantity 1 minus alpha squared times P naught. Again, P naught is 1 bar, just to make our quantity here unitless. And then we can solve that for alpha. So alpha is the square root of 1 over 1 plus 4p over k p naught. So even though our equilibrium constant K is independent of the pressure, total pressure P, the amounts of A and B do in fact depend on the pressure. Right? So alpha, how much of our A has reacted, depends on the total pressure P, even though the value of K does not. So as the pressure P increases, as we increase the value of P here, the value for alpha decreases, which makes sense, right? We said that if we go from 1 mole of A to 2 moles of B, that Le Chatelier's principle says that we should be shifting back towards A if we compress our mixture. On the other hand, if we expand the mixture, we should be shifting towards the product side and getting more P. So as the pressure is increasing, as P is increasing, we are decreasing alpha. Again, alpha was the amount of A that reacts. So if we're decreasing the amount of A that reacts, that means we're really getting more of their A back. And so that agrees with Le Chatelier's principle. So if the temperature is increased, now Le Chatelier's principle predicts that our equilibrium will shift in the direction of the endothermic process to oppose the change in temperature, right? So energy is absorbed as heat in the endothermic process, so the endothermic process should occur more, and that will shift our equilibrium position in that direction. So on the other hand, if the temperature decreases, Le Chatelier's principle predicts that the equilibrium will shift in the direction of the exothermic process to produce a little bit more heat and oppose our change in temperature. So again, in the exothermic process, energy is released as heat. So remember that the temperature is still going to change. If we're raising the temperature will still rise, even though some of that heat, because only a portion of that heat is going into our reaction. We aren't able to use all of that extra heat that was added in the reaction. So we can summarize these like this. So for exothermic reactions, increased temperatures favors reactants, and for endothermic reactions, increased temperature favors our products. Right? So if our reaction is going to absorb energy, so it's endothermic, if we heat it up, we're going to get more of our products. If our reaction releases energy, if we heat it up, we're going to get more of our reactants, less of our products. Right? This makes sense. So for an exothermic reaction, to get more of our products, we want to cool it down. For an endothermic reaction, we want to heat it up. So this brings us to the Van 't Hoff equation. So this is derived in the book. I'm not going to go through the derivation here, but this is an expression for the slope of our equilibrium constant as a function of temperature, and it can be expressed in two different ways. So we can either express it like this. So the change in the natural log of our equilibrium constant K with respect to temperature is equal to our standard enthalpy of reaction, delta RH, divided by R times T squared. Or we can show it this way. So we can remove the temperature from the right side here, basically, and get the change in the natural log of our equilibrium constant K with respect to 1 over temperature is equal to minus the standard enthalpy of reaction divided by R. So for an exothermic reaction at standard conditions, our enthalpy of reaction is less than 0. Our standard enthalpy of reaction is less than 0. And this means that now our slope of natural log of K with respect to temperature is less than 0. And this means that the slope of our equilibrium constant K with respect to temperature is less than 0. And a negative slope means that our equilibrium constant K decreases as temperature increases. And that means that reactants are favored as temperature increases. On the other hand, for an endothermic reaction, our standard at standard conditions are delta R H naught. So our standard enthalpy of reaction is greater than 0 because we have to put in energy to get this to happen. So now the slope of the natural log of K with respect to temperature is greater than 0, and that means that the slope of K with respect to temperature is greater than 0. And a positive slope means that our equilibrium constant K increases as our temperature increases. Which means as we increase the temperature, because K is increasing, we're getting more of our products. So more products are favored as we increase the temperature. So remember that the standard Gibbs energy of reaction is equal to the standard enthalpy of reaction minus the temperature times the standard entropy of reaction. We can rearrange this, so if we divide everything by the temperature, we get delta Rg naught over T is equal to delta Rh naught over T minus delta Rs naught. So For an exothermic reaction, this quantity, the minus delta R H naught over T, is greater than 0. And that means that the change in entropy of our surroundings is positive, and this favors the formation of our products. If the temperature then increases, our fraction here decreases, and the increase of our entropy of the surroundings decreases. And that means that then we can say that the driving force to form our products is smaller, and the equilibrium position lies farther to the left. On the other hand, for an endothermic reaction, our fraction here is less than 0, and that means that the change in entropy of the surroundings is negative, and this means that the driving force for the reaction is the increase in entropy of the system, and the increase in entropy of the system has to be larger than the decrease in entropy of our surroundings for our reaction to occur. Which means, as the temperature increases, our fraction here decreases, and that means that the opposition to the reaction decreases, and our equilibrium lies farther to the right. We get more of our products. So, again, we can explain these results using a molecular approach. So, remember that the molecules involved in a reaction can have a Boltzmann distribution over the available energy levels. So, in this case, we have some Boltzmann energy levels, or some Boltzmann distribution amongst the energy levels, the microstates of A. Note that A has a lower minimum energy here than B does. So here we have an endothermic reaction. So again, this is an endothermic reaction at low temperature. Now our low energy states have higher populations. So again, at low temperatures, these lower energy states have higher populations, and that means that we have more of our molecules in our A states and fewer of our molecules in our B states. As we increase the temperature, then we spread out our populated states, and we're decreasing the fraction of our population that is down here in the low energy states. So we're decreasing the population that is in the A and putting more of our population up into the states that are sub B. So again, as the temperature increases, this means that the populations of our low energy states are decreasing, populations of the high energy states are increasing, which means higher population states in B at the expense of some population of A, and that means that we're removing some of our A and getting more of our B, and that means that our equilibrium position has to be shifting to the right when we heat it, again for an endothermic. Here we have an exothermic reaction, so in this case, as we move from A to B, it's exothermic. So, in this case, at low temperature, the lower energy states, so these, now the lower energy states are those from B, our product. So at low energy, now, or at low temperature, now we have more of our population in B, that's our product. So low energy, or low temperature should lead to more of our product. And as the temperature increases, populations of the low energy states again are shifted up into some of the higher energy states. So we're losing some of our B, getting back some of our A. We're moving back to our reactant side. And this matches what we see with Le Chatelier's principle and what we predicted mathematically. So, if we want to find the value of equilibrium constant K2 at some temperature T2, using the value of the equilibrium constant K1 at some other temperature, some initial temperature, T1, we now can integrate between our two temperatures. And so we get the natural log of our equilibrium constant at the second temperature, K2, minus the natural log of our equilibrium constant at the first temperature, K1, is equal to minus the inverse of our gas constant R times the integral from 1 over T1 to 1 over T2 of the standard enthalpy of reaction times the change in our temperature, so d1 over t. So So if we're assuming that our our standard enthalpy of reaction changes only slightly with the temperature, or at least over the temperature range that we're looking at, then we can move it outside the integral, and that means that we get this, and so now we can evaluate that integral, and so now we have our difference between natural log of our two equilibrium constants is equal to minus the standard enthalpy of reaction divided by R times the quantity 1 over T2 minus 1 over T1. That was the response of equilibria to conditions.